Yeah, you're good.
Okay, thank you. All right, so Friday, January 12th, see, lecture 3. We stopped right here. All right, anyone have any questions so far? Okay, let's pick up with Ohm's law. So I assume several of, well, actually, if you have taken Physics 133 or Physics 3, you should be familiar with Ohm's law. Some of you may have even encountered this in high school, right? It's the fundamental, it's one of the most fundamental laws in electrical engineering. Again, George Ohm was the one who did a lot of work in this. And so he discovered this equation, created it. V equals IR came to be named after him. Voltage is the product of the current and the resistor. So using this equation, we will build upon this equation. We'll learn new techniques. And I mentioned in last class that you could solve any circuit based on this equation. Well, that is true and also not true at the same time. There will be some circuit connections that will kind of make it very difficult, if not nearly impossible, to actually solve it just using this one equation. And so over the years, over decades, lots of research has been done. Lots of people have come up with their own methods to solve different kinds of circuits. And we will learn about some of these methods as we go along. But this is the most fundamental of equations in electrical engineering to solve for unknown quantities in an electrical circuit. Voltage is equal to the product of the current that flows through a resistance. V equals IR. In units, volts is equal to amps times ohms. And from this equation, we can rearrange the terms and we can determine current if you are given the voltage and the resistance, or we can determine resistance if we have the voltage and the current, right? Any questions before I go further? Okay. All right, so then we come to energy and power, right? Electrical circuits, we talk about electrical energy, right? But the law of conservation of energy still applies. Within a circuit, if there is a source that is supplying some energy, that energy is either consumed by the load or is dissipated as heat. We cannot escape heat, okay? There are some electrical circuits or electronic circuits where heat is a big factor. If you ever seen the inside of a desktop computer, you might have seen a massive heat sink that sits right on top of the CPU. Anyone ever seen that? Right? Even in laptops, you had, like nowadays, of course, microchips are so efficient that they do a really good job of not heating up. But you always seen these older laptops that have huge fans running in them. Nowadays, not so much. But the reason for that is that a CPU has billions and billions of transistors. They each release like nanowatts, microwatts or nanowatts of energy as heat. But when you have a billion of them releasing like 1 nanowatt each, it turns into like 10 or 15 watts of heat dissipation. And that's why you have these massive heat sinks and fans inside a computer. And so again, electrical energy, if a source is supplying some energy, a lot of it is consumed by the load. The load could be resistors, capacitors, inductors, transistors, solid state devices. And along with it, a lot of it is lost as heat. So when it comes to an electrical circuit, as I said, current and voltage are always together. If current flows through a circuit, voltage appears across that element. If there is voltage applied across an element, we'd have current flowing through that element. Okay. Energy is transferred from source to the load. And the only load that we study in this class is a resistor, capacitor, and inductor. So when we get to chapters 3 and onward, we will look at how energy is transferred from the source to a capacitor to an inductor. And in chapters 1 and 2, we look at how energy is transferred to a resistor. When energy is transferred, you have voltage and current, appearing at different parts in the circuit. So our job would be to figure out what the values are for that voltage and current, and then the associated power and the associated energy. Electrical power is given by this equation, V times I. P is equal to VI. Okay, P is equal to VI. So it doesn't matter what the component is, whether it's a resistor, a capacitor, or an inductor, you would use this equation. P equals V times I. Power is the product of the voltage and the current for that element, for that particular element. Now, if you think a few slides ago, I said, when we first begin analysis, we have no idea which direction the current is flowing, what polarity a voltage might have across an element, right? So we apply these values randomly. We would assign polarity to a voltage, and we would assign direction to a current flow through an element randomly. We make an assumption, but these assumptions are based on certain logic, and I will explain that logic. When it comes to energy and power, if we have assumed that this element has a minus here and a plus here, meaning the polarity of the voltage is assumed as shown in this figure, and if we assume the current is flowing in this direction, then we can make a guess, or we can actually have a conclusion from that assumption that the current is actually going from the minus to the positive terminal. And so if that's the case, then the energy is being supplied by that element. Again, if the current direction, whether it's assumed or whether it's known, is showing that the current is going from the negative end of an element to the positive end of that element, then the energy is being supplied. Okay. This minus and this plus sign is showing the polarity of the voltage. And this is showing the current flow. So whether the current direction, whether the voltage polarity is provided to you, or whether you are assuming it, is irrelevant. Once you have these two pieces of information, the direction of the current and the polarity of the voltage, then you can conclude that if the current is going from minus to plus, the energy is being supplied. If it goes from plus to minus, energy is being absorbed by that element. Yes. Well, positive and negative is just for us to actually make calculations. So if it's a power supply supplying energy. Is, if you ever look at an adapter, it will say, it's a 10-watt adapter, meaning a power supply supplying 10 watts, right? But it's not a positive or a negative per se. It is actually supplying 10 watts. But for us to balance out our equations, we say that anything that supplies power or anything that supplies energy is negative, because it is losing, right? It is supplying energy, it is supplying power. So it's kind of like losing energy. And so we put a negative sign in front of it. But in real life, it's not a negative, right? So the question being asked was, how do we know it's plus or minus? And so again, we use plus and minus to note for the mathematical equations. Otherwise, our equations would never balance out. If you have a power supply, and we know that the power supply is supplying some amount of voltage and some amount of current, then we can calculate the power that it is supplying. So if there is one source in a circuit and let's say 2 resistors, we would know that the power supply is supplying 10 watts. And perhaps the 2 resistors are absorbing, receiving 6 watts and 4 watts each. Then we can say 10 watts being supplied is equal to 6 being received plus 4 being received. If we didn't put a negative sign on that 10 that is being supplied, our equation would never balance out. Does that make sense? And once we solve examples, it'll become a lot more clear. Does that answer your question? Okay. All right, so energy is supplied if the current goes from the negative end of the voltage polarity to the positive end, and it is absorbed if it goes from positive to negative. Passive reference configuration. Again, this is just simply showing you what equation you would choose if the current enters the positive or the negative terminals. So if you see this in a problem, okay, again, whether this information is supplied to you or whether you're making an assumption is irrelevant. Once you have this information, meaning the polarity of the voltage and the direction of the current, now you decide what equation you need to use, okay, based on these assumptions or information. So in this first one right here, this is plus, right? So this element is plus at the top and minus at the bottom. The polarity of the voltage is plus at the top and minus at the bottom. And the current direction is already given to us. It is entering the positive terminal. So power is positive. You would use the equation P equals VI. P equals VI. Make sense? So power is positive. Okay. If we look at this image right here on the far right, the current is now entering the negative terminal. So if this is minus right here, this is plus right there. Current enters the negative terminal of that element or negative polarity of that voltage. The element itself does not have any polarity. It's the voltage across that element. So current is entering the negative end. And so power is negative. If power is negative, you would use the equation P equals minus VI. Okay. In real life, again, power is never negative or positive. It's simply for us to actually solve circuits. You would say power is being supplied. You put a negative sign in front of it. If power is being received, it's positive. Think of it as money. If you lend $100 to your friend, most likely you'll never see it again. And so you're now out of $100. So that's a net negative on your bank balance. If you receive 100, then it's a net positive. So again, if you're supplying energy, if you're supplying power, it's negative. If you're receiving energy, if you're receiving power, then it's positive. Make sense? Let's look at images B and C. Here we see that the current is leaving the negative terminal. If it's leaving the negative terminal, I would simply extend that arrow. You extend it, and you can see that it is entering the positive terminal. So power is positive. And the same thing here. If we extend the arrow, we see the current is entering the negative terminal and power is negative. Let's take a 10-second pause, think over it, and let me know if you have any questions. Yes. Not necessarily. We'll look at some examples and you will see that it's going to be different. It could end up being that the voltage that is provided to us. So the question being asked is, will the voltage and current always be positive if we encounter these kind of circuits? And the answer is no. The value of the voltage or the value of the current could end up being negative also. And we will see that in just a few slides. Yes. Yes, that is absolutely correct. The question being asked was if the current value was given to us as negative, then would it mean that the flow of the current or the arrow should be switched? And the answer is yes, absolutely. A negative for a current or a voltage simply means that the direction or the polarity is switched. That's all it means. And again, when you solve problems, if you end up with a number that is negative, it does not mean that your answer is incorrect. Okay, it would simply mean that your assumption that you made at the beginning of the problem just means it would be flipped. That's all. As long as the numerical value is the same, you would still get full credit. All right, moving on. So examples right here, we are given voltages VA, VB, and VC, and we are also given the three current directions, IA, IB, and IC. So in the first one, IA is entering the positive terminal. So power is positive. We would use the equation P equals VI. This would simply be 12 times 2, 24 watts. So this is how I would expect students to set up the problem. Okay, you write down the equation first, then you would enter the values, and then the final answer along with the units. Do not forget the units. Okay, if the units are missing, 1 point will be deducted. As engineers in your own field, you should know and understand that units are very important. Okay. Otherwise, I could take this as 24 milliwatts, 24 microwatts, 24 volts. I have no basis of assessing your knowledge, right? So units are extremely important. Units and unit prefixes. How about the second one? I heard some murmurings. You can be confident in answering. I'm not going to deduct any points. So it's entering. So I heard negative from somewhere, right? So it is. If you extend the arrow, it's entering the minus terminal. So it is indeed negative. And so for the second one, P equals minus VI. All right, P equals minus 12 times 1. And therefore, P is minus 12 watt. We don't know what these elements are. We don't know what A, B, and C are. A could be a resistor, capacitor, inductor. But if the power for an element comes out to be negative, we can be sure that it is supplying power, it's supplying energy. So it is a source. We don't know what kind of source it is. It's either a voltage source or current source. But if a power associated with an element is negative, it is a source. And then here we circle back to that question that was being asked earlier. So what is the power equation we use for C? P equals VI because it is positive, right? It enters the positive terminal. And so P equals VI, but the value of the current given to us is negative. So we simply enter the negative value here. We do not mess with the direction of the current. The current direction is what it is shown in the figure. We are not concerned with that. Okay. It does not make your analysis incorrect. It does not render your answer incorrect. It simply means that the current is flowing in the opposite direction of what it is shown. So do not get bogged down into the direction of the current and the polarity of the voltage. Again, I repeat, it doesn't matter what you assume at the beginning of the problem. As long as your method and your calculations are correct, at the end of your solution, at the end of your analysis, you will end up with the right answer. So the answer in this case is minus 36 watts. Okay. Current enters the positive terminal. So the equation we use is positive P equals VI. Then we substitute or plug in the values. V is 12 volts. Current is minus 3. Current is minus 3. So we end up with minus 36. All right, let's take a pause. Let me know if you have any questions. Is this clear? Yes. Yes, that is correct. Yes. Question being asked is which elements are absorbing and which one are supplying energy? And the answer is if your eventual answer for power is positive, then the energy is being received, energy is being absorbed. If your eventual answer is negative, as we see for B and C, which is minus 12 and minus 36 watts, then energy is being supplied. Power is being supplied, energy is being supplied. I can note it right here. Received or absorbed, supplied, or delivered for B and C. Okay. Moving on to the next one. Any other questions? All right. How do you say this name? Kirchhoff, right? So I'm from India. When we first learned this, we pronounce it as Kirchhoff. And apparently it's a German physicist. The actual German pronunciation for this name is Kirchhoff. So none of us were alive during his time, so we don't know. But the first time I heard this name was in a department meeting, and someone kept saying Kirchhoff, and I was like, I have no idea what that means. What do I do now? And then it turns out they're talking about KCL and KVL. So if you hear me use the word Kirchhoff, this is what I'm talking about. German physicist who came up with two equations, two laws, one for voltage and one for current, came to be named after him, and we use the acronym KCL and KVL. Assume again, students have done this before in physics. Yes, no, you might have forgotten, but that's not a concern. I will recap and we'll go over it again. Basically, it again derives from the law of conservation of energy, for both for current and for voltage. It's brilliant in its elegance, actually. It basically states that if you have a closed loop electrical circuit and you have a junction in a circuit, a junction basically a point or a node where two or more conductors meet, then the currents entering the terminal would be equal, or the sum of the currents entering the terminal have to equal the sum of the currents leaving the terminal. So in simple terms, if you have a junction like this, and you have two currents entering and two currents leaving, then the sum of the currents entering the node or the junction is equal to the sum of the currents leaving the junction. As easy as that. Imagine this is a traffic light. Okay, if this is a traffic light, all vehicles entering the junction have to equal the vehicles that leave the junction. Otherwise, you'd have Die Hard 4. Anyone seen that movie? Where all lights are green? Not possible, right? So again, all vehicles that enter a traffic junction have to leave. Otherwise, well, it would not work. So in this example, we are given IA as 6 amps right here. IC is given as -2. ID and IB are unknown. And so is IE. So let's solve for that. Okay. Now, IC is given as negative, but you do not want to go in and try to change the direction of the current. You can if you want to. Okay. But it might just end up causing confusion. So just stick with the information that is provided to us, and we will just analyze it based on that information. So first thing to note is on the left right here, IA and IE. What do you see? They are actually in the same circular path, right? Right here. It's the same exact electrical path. From this point to this point, it is one single electrical path. Again, think of it as a road or a street. It's a single street. If IA is going in this direction and IE is going in the opposite direction, it means IA is equal to minus IE, or IE is equal to minus IA. Same equation, just flip it around on either side. Okay, so looking at the first thing in the example, I can write IA equals minus IE, or IE equals minus IA. As easy as that. And since IA is given to us, I can write IE is minus 6 amps. Make sense to everyone? They're the exact same current. They're just moving. They're shown to be moving in different directions. In real life, this is not possible. Okay, in real life, this is not possible. If you have a current going physically in one, I mean, we are not in a physics class, so we don't delve too deep into the physics of this. But if you have electrons moving in one direction, you cannot have a current moving in the opposite direction. Okay, so there is a current that's established moving in one direction. It will be exactly the same direction. So physical basis in real life, you cannot have two currents going in opposite direction in the same electrical circuit. Not unless it's alternating, but that's different. So this arrow and this arrow that you see right here for IA and IB are purely theoretical. If these were not given to you and you were trying to solve a problem, logically, you would make an assumption that both currents are in the same direction. You would never choose something that goes in the opposite direction. So just wanted to point that out. This is just an example to show how KCL would work. All right, so let's come to this junction now. We know IA, we know IB, we know IC. So we know the currents that are entering this junction. We know IB is leaving. What equation can we write from this information? Sum of currents entering the junction should be totaled up. And what I do is, once I start writing out an equation, I just put an equal to sign. And then every current that is entering the junction, I put on the left-hand side of the equation. And then every current that's leaving the junction, I put it on the right-hand side of the equation. So the currents that are entering the junction are IA and IC. And the only current leaving the junction is IB. So that goes on the right-hand side of the equation. And that's it. I have my KCL. I have my KCL equation. Sorry. Make sense? Now, if you remember KCL from your previous classes and you already have a particular method or a particular technique that you'd like to use, that is fine. I will not deduct points if you do not use this exact same technique. Okay, as long as KCL is applied correctly, that's all I care about. because there is also another way to write this equation out, which is basically the sum of all the currents entering or leaving the junction is equal to 0. And so one technique is to actually assign a minus or a plus sign to the current. Meaning if the currents are entering, you take it as positive. If the currents are leaving, you take it as a negative. The equation would come out to be IA plus IC minus IB is equal to 0. Same equation. Just a different technique, but it's the exact same equation. Does that make sense? Right? So again, use whichever technique you want. I don't really care. As long as the KCL method is applied correctly, you will receive full credit. And so in this case, I have IB as equal to 6 plus minus 2. Remember, IC is given to us as minus 2. So 6 plus minus 2 gives us IB as 4 amps. Easy enough, right? Then last we come to ID. ID is simply entering this junction, IB is entering, and IE is entering. Now we have diehard 4. All three of them are entering the junction, which is not physically possible, right? But again, if you're given these directions, you stick with those. You do not change them mid-problem. Any assumption that you make at the beginning of your analysis, you stick with it right till the end. If you change your assumptions in the middle of your analysis, you will end up with the wrong answer. So do not do that. Okay. So in this case, since all currents are entering, I will write ID plus IB plus IE equals to 0. I take it on the other side of the equation. I get ID equals minus IB minus IE. IB is 4, so minus 4, and IE was minus 6. So I get ID as 2 amps. I take a pause while you write that down. Think over it and let me know if you have questions. Yes. No, because it's not where you are correct. All these years that I've solved this, I never noticed that, never pointed it out. No one pointed it out. Okay, so the question being asked is, on the left side of the circuit, we had A and E, right? A and E that are going in opposite directions. And we have the same on the right-hand side of the circuit, just C and D. Does everyone see that now? How many of you noticed it before? You should have spoken up. I can't believe I've been solving this for like, no, more than 10 years. I never noticed it. And no one ever pointed it out. So again, speak up if you see something, if you think I made an error or mistake, or if you think you didn't understand something, just speak up. But anyway, this was not an error or anything. This was just a long-winded way of solving ID. Since you already solved IC, ID and IC are in the same branch of the circuit. They're just moving in opposite directions. Exact same scenario as A and E. And so ID can directly be written down as minus IC. And IC was given to us originally as minus 2 amps. We would simply write ID equals minus IC, which is simply 2 amps. So remember, on the first day of class, I mentioned that there are many different ways to solve a problem, right? But if I ask you for a specific method, then you have to show me your knowledge of that method. Otherwise, I will not be able to evaluate it. So if I ask you to solve a problem, let's say using Ohm's law, but you use something else, then I would not be able to assess your knowledge of Ohm's law, and I would not be able to give you the full credit. So in this case, we can directly write down ID. It's a small example. It's not, it doesn't make sense in the larger scheme of things. We can directly write down ID is equal to IC, or we can solve it using like multiple steps using KCL. All right, any other questions? All right, let's move on. KVL. Actually, let's do KVL here. So I'll assign this as practice. Simple enough. You have one junction, 4 currents, 3 in the first one, 4 in B and C. Just do it at your own time. If you have any questions or doubts, you let me know. But again, as far as KCL goes, it's easy enough. Okay. Let's come to KVL, Kirchhoff's voltage law. Again, based on the law of conservation of energy. It's brilliant actually, because it states that if you have an electrical loop, doesn't matter what kind of loop it is, if you add up the voltages around that loop, they will all sum up to 0. And again, as with KCL, if you have a preferred method of applying KVL, I'm not here to disrupt that. You are free to choose and stick with what you know. As long as the equation is correct, I will give you full credit. Okay. KVL simply states, if you add up the voltages around a closed electrical loop, the voltages will always sum up to 0. So it's a closed electrical loop. Everything in that loop could be a load, or it could be a source and a load. But if you add up the voltages, will add up to 0. So let's take a look. Let's take a look at these loops. So electrical loop is basically if you start at one point and you travel down the street and you come back at the exact same point, that is a closed electrical loop. So we start at the bottom left corner in this circuit and we go around. We go to A through B to C, and there's a pathway to come back to that point. So we have one electrical loop, loop 1. If we start at the bottom left corner and we keep going, there is another pathway to come back to that same point of origin. And so that is loop 3 in this example. And then, of course, we have the other junction, the other node. Now, my preference is always to start at the bottom left corner, but it doesn't really matter where you start. I travel around, and that is loop 2, noted in this example. So we have 3 electrical loops. And the brilliance of this principle is that it doesn't matter which loop you choose, if you add up the voltages in that loop, they will always sum up to 0. Yes. Doesn't really matter the direction. So the question being asked is the direction of the loops. It doesn't really matter. The direction is basically the direction in which I choose to add up these voltages. So here you see it's like clockwise, and then loop 3 is like counterclockwise. It doesn't really matter. So KVL does get a little bit, it has an extra step more than KCL. KCL is rather straightforward. Currents entering a junction equal currents leaving a junction. Voltages, not so much. The way I apply KVL is this. So if you take loop 1, we have A, we have B, and we have C. Right? A has a polarity like this. This is B, and this is C. Now you can start at any corner. You can start between A and B, or between B and C, or between A and C. My preference, again, is always to start at the bottom left corner of the schematic. So I start from here, and I travel around that loop. Okay, I travel around that loop. Now, when you add the voltages, you can choose to go clockwise, or you can choose to go counterclockwise. It does not matter. It is not a current direction. That arrow simply points out which direction you're adding the voltages. That's all. I always go clockwise from the bottom left corner. So as I travel around that loop in a clockwise direction from the bottom left corner, I encounter voltage VA, VB, and VC, right? 3 voltages. So I need to have VA, VB, and VC written out, and they should all equal 0. Okay, that's the first thing I do. I just write down all the voltages that are there in the loop, and they should all equal 0. We good so far? Then I simply look at the point of entry. Again, this is not the current. The arrows that you see here is simply me adding up the voltages. It's not a current direction. It's just me going around the loop, trying to add the voltages. So the first voltage I encounter is VA, and I'm entering through the negative terminal. So I put a minus in front of VA. That's it, as simple as that. Then I leave VA, I encounter VB. VB, I'm entering through the positive end, and so I put positive. I exit VB, and I come through C. I'm entering the positive end of C, put a plus sign in front of C, and that's it. I have my KVL equation. Minus VA plus VB plus VC equals 0. We'll take a pause and let that sink in. And again, it doesn't matter how you are used to applying KVL. If you have a preferred method that you already use, a lot of you I know would have done this in high school within Physics 3. I'm not here to erase that. You stick with what works for you. As long as you have the right equation, I'll give you full points. Does it make sense? Let's add it up from the other direction. Okay. This is for clockwise, and this is for counterclockwise. If I go counterclockwise from the bottom left, the first voltage I encounter is C. So again, let me write down 3 voltages, VA, VB, and VC equal to 0. If I go counterclockwise, I'm entering the negative end of C first. So I will put down a minus in front of C. Then I encounter the negative end of B. So I'm entering through the negative end. I put down a minus in front of V. And then finally, VA, I'm entering through the top, positive, plus VA. So again, plus VA minus VB minus VC equals 0. Exact same equation, no difference. So it does not matter which direction you choose to add up the voltages when you apply KVL. Make sense? Right? So this is how I do it. Just take a loop, note down the voltages, put equals to 0, and then just travel around the loop. Look at what the point of entry is. If the point of entry is minus, you put a minus in front of that voltage. If the point of entry is plus, you put a plus in front of the voltage, and you have your KVL equation. Now, the reason I'm going slowly and a step by step and explaining this is because this entire class, specifically chapters 1 and 2, are built step by step, more than any other class that you've ever seen. Okay, we start with Ohm's law, V equals IR, power equation, P equals VI. Then we start with KVL and KCL. When we move to chapter 2, you will apply KVL and KCL to another analysis technique, node voltage analysis and mesh current analysis. So you need to be proficient at applying KVL and KCL correctly and quickly. And so that's why I have separate homeworks for each. So students need to be proficient at applying both KVL and KCL. You need to practice so that it becomes like second nature, because we will build on these. We will use these principles and apply it to a different method. Right, so I want to be absolutely clear. That's the reason why I have separate homework for those. Otherwise, it seems like a very simple topic, right? Again, the point is that students should be able to apply these quickly and efficiently and correctly. All right, any questions? Okay, then let's example right here. I will assign as practice. Okay, do this, and if you have any questions, let me solve the first one on the left. How much time do we have? 9:56. So actually 2 more slides I need to do. Oh, not here. So I'll keep it for practice for now, just in the interest of saving time and completing this chapter. If you have any questions, you let me know, right? What I'm going to cover is parallel connections. Kirchhoff's current law and series connections. We already saw series, but I'll point it out again. Okay, series connections are like holding hands. Okay, they're like holding hands. That's how I like to describe it. If you have 2 terminal elements, which by the way, in this class, we only see 2 terminal elements. Resistors, capacitors, inductors, they all have 2 terminals and they are not polarized. Okay, either end could have plus or minus, right? If you apply a current to a resistor, depending on the power supply polarity, there will be a current direction that flows through that resistor and the polarity of the voltage that appears across that resistor. But it itself inherently does not have any polarity. So a capacitor, a inductor, and a resistor all have only 2 terminals and they do not have any polarity. So if you take any 2 elements and you join them together, so this is 2 terminals for each element, and you join or you combine one end of each element to each other, we call it a series connection right here. So a series connection should not have more than 2 connections at that junction. If it's more than 2, then it's no longer series. So it should not have more than 2. No more than 2 connections, or 2 elements actually. Let's put it that way. No more than 2 elements. Otherwise, it is no longer in series. Okay. Parallel connections is if you take both terminals of those 2 elements and connect them to each other. So if you have element A and element B, element A and element B, again, both of them have 2 terminals each. You connect those 2 together, and they are said to be in parallel. If there is something else in between those connections, then it is no longer in parallel. Okay, so series connections are if you hold one hand each, and parallel connections are if you held both hands. So they are like holding hands. That's how I like to explain that. If you look at this example right here, elements A and B have 2 terminals each, and their respective terminals are connected together. So A and B are said to be in parallel. and so are D, E, and F. Okay. One final thing. If you combine A and B together and make it as if it's AB, and you combine D, E, F together, D, E, F together. Now, element AB is connected by one terminal to C, and DEF is also connected by one terminal to C. And here at the bottom, A, B are connected to DEF by just one terminal each. Then we say all three of these are in series. Okay, all three of them are in series. So on that note, we will end here today. This is the end of chapter 1. Let me know if you have any questions. I do not have any office hours today. There is a employee orientation and paperwork that I have to go sign. There's a lot of other things that get done, but I will be available via email and via Zoom. Okay, so let me know if you need to see me. All right, have a good weekend, and I will see you all on Tuesday. Tuesday, don't forget that.
Thank you.
Let me stop this.